Alright, tonight we're going to look at elevator design. This is a really common problem that we have in FRC games. Um, if they're not the main scoring element, so like in 2018 and 19, you basically needed elevators to score. Um, they are often used in the end game for any sort of climbing device. So if we need to be able to like reach up and grab a bar and do a chin up or a pull up, or if we need to um, lift something else up, or anytime we just need to move the height of the robot, we're probably building some type of elevator. And there's some differences and uniqueness that goes into each one, but they all kind of work on the same basic principles. We're always trying to move a portion of the robot higher, straight up and down, kind of like a forklift. Um, in theory, there's reasons there might be a game where we need to make them to where they're not straight up and down. Maybe we like turn the elevator at some angle or sideways. Maybe you want to reach really far out. You could build an elevator that's like kind of sideways to reach far out. We've never really needed that in FRC, but there's been games in like FTC where that's been an option. Um, so anytime you just need to like extend it, they're kind of like, right, you can see what it looks like. It's kind of like a powered drawer slide is kind of what they look like. But we almost always in FRC, because they have to handle so much weight, we're always going to build them ourselves out of kind of raw materials and bearings and things. We're not going to use off the shelf drawer slides very often for elevators. There's a few teams who have made it work, and we've investigated it a few times in different years. Most of the time, we come back to trying to build our own thing. And normally, you can make it a little bit more specific to our application each time. So this is photos from 2019. So this is the 2019 elevator CAD here, or like a simple version of it. And this is the 2019 robot. And so we have the elevator that you can see in the animation on the right going up and down. So we can actually get to all three of those scoring locations with the robot. The specific elevator we're going to look at tonight to kind of go through is a product that you can buy. So this is called the Greyt elevator. Greyt is spelled that way because it's based off of the Greybots, which are a team. And one of their mentors helps design these products. And so this specific elevator design is very simple to make. We probably would never buy the full kit, but a lot of times it's very similar to the elevators that we've built throughout the years. And it kind of just has some of the best practices of designing elevators for FRC built into it. So it's a really good, clean example of what we can do with an FRC elevator. There's also elevator kits sold by other vendors. They're all relatively similar. This one has a really clean model that I like using and was able to get the cat out of and stuff, so we use this one. But there are other vendors who do a similar thing. And like I said, most of the time for us, we're going to be designing our own a little bit just to tweak it and get it to exactly the kind of features and function and fit that we want on our robot. Okay, so one of the first things to think about with elevators is they have stages. So this part down here that's in red is what we'll normally call the tower sometimes. We'll also call it like the base stage sometimes. And it's completely stationary. So this doesn't move relative to the robot, relative to like the robot's drive base. It's attached to the frame. It's kind of how we mount the whole elevator. So we'll mount this bar down here to the actual robot chassis, or sometimes we'll even mount like these outside bars to the chassis itself instead of having this bottom crossbar. Then we'll normally mount the part that powers the elevator and moves it up and down. Like the motors will also be mounted to this tower or base stage. The first stage is here in this light purple, so it's another big frame going out across the whole kind of middle of the elevator. And it's the large moving stage. So you normally have this second kind of big rectangle, and so this is normally called the first stage because it's the first moving part. And then in green, we have, in this case, this is the final stage. So the final stage of an elevator is normally called the carriage. In this case, it happens to be the second stage. But like this note down here says, you can have an elevator with more stages. So you can have a 3-stage elevator or a 4-stage elevator. And then you'd basically have this frame. You'd have another one of these frames inside of it. You'd have to make them They wouldn't be allowed to have like this kind of top. They wouldn't be allowed to close it. They'd have to be closer to like this outer tower, but it would move up and down. And then you'd have multiple stages that can get you even higher. So you can get to a much higher reach. If you had to reach an object instead of like 9 or 10 feet, like we have to do in some games, maybe you had to reach up to like 12 or 14 feet for some really tall stacking game or something. You could have multiple stage elevators to help you do that. Or if you needed to be able to come down and your starting height needed to be a lot lower. So to be able to get a lot more reach out of a much lower starting height, you would have more stages to be able to expand even further. So it just kind of depends on the requirements for the game and what we're trying to do with the robot. But either way, the final moving stage and kind of where normally the manipulator or anything's going to be mounted to is normally called the carriage. It's the important part that kind of keeps the rest has all the mechanism stuff, and normally our manipulator or intake or whatever is going to be mounted to the carriage. It's normally designed a little bit differently too because it's a lot smaller and normally rides completely inside. Okay, so these are some details that aren't necessarily elevator specific, but there's things I just want to make sure we've covered. So the Greyt elevator is put together using gusset and tube. When we say gusset, all we really mean is a flat plate normally. Sometimes if you have a bent gusset, they're not flat anymore. But if they're normally just saying attach it with a gusset, we normally mean flat unless we add some descriptor to it. And we're just connecting 2 or more parts. So they have like hole patterns built into them. So these are parts that we can buy sometimes. We'll also make our own. We can make plastic or wood ones on the laser cutter. We can make metal ones on the CNC router. And these allow us to quickly assemble tubes together. And this is one of the most common ways we build mechanisms in FIRST Robotics is using this gusset and tube style. And just like we've done with some of our projects throughout the semester, we use rivets to hold these together because anytime we're going into a tube, it's a lot harder than you don't necessarily want to have to bolt all the way through. It's a little bit more complicated. It takes more time. So we'll use rivets, which I'm not going to go over too much because we've previously on this thing, this was one of the first time we introduced rivets, but most of you should have already popped rivets in our in-person work. But rivets are there to make sure you don't have to access the other side of the tube, and we can secure the gussets easily to the tube very strongly, very securely. And this is largely how like our entire robots gets created, or large portions of it at least. Just like almost everything in our robots, if it's moving, it probably has a bearing involved, or at least there's some type of bearing. So we try to use roller bearings whenever possible. So if we were on the call last week, we talked about roller bearings inside of the kit of parts drivetrain. They have that inner race that's spinning, and the outer race is able to stay stationary, and it's rolling on these balls on the inside. So this allows us to have a very low friction and allows us to spin really, really nicely. In the elevator, we'll actually use them kind of inside out. So we'll use the outside to spin freely because it's going to be rolling kind of along one of the parts of the elevator. We're going to use the outside almost like a wheel. And so the inside will be like bolted up nice and tight. And the outside of the bearing will spin really freely and allow it to slide very, very cleanly up and down the parts of our elevator. Not all elevators have to use bearings. So the other type of bearing, instead of like a rotary ball bearing in this case, is you can make bearing surfaces, or they also sell linear bearings for certain type of mechanisms where really all they're doing is trying to reduce friction between them, but they're not going to have most of the time the rolling surfaces. So there's some specific like linear rails and things that have recirculating ball bearings that can do linear travel that you might see in in certain drawer slides or in some of the motion products that we have in the lab. So like our CNC router and things will use some of those types of bearings, but a lot of times they're too heavy or complicated for what we need to do in FRC. Sometimes they're too expensive. There's also just, instead of using ball bearings at all, instead of having these little balls, again, the concept of using a bearing is just to reduce friction. So there's ways to do that that don't involve using the ball. So you can use certain plastics and other materials that just have very low friction, right? You've felt slippery plastic before. So there's a variety of material types that have a low coefficient of friction against either themselves or against certain metals. So some teams will build up part of the elevator bearing surface to where we just have a plain bearing surface, which is just a slick material that's sliding up and down on the elevator rails, and that's what moves it up and down. Depending on exactly how much force is or how much load, like if you're trying to like pull the whole robot weight up with it, you may not want to do that because it can still bind. Just like if you've ever used like a really old drawer, if you put a lot of weight in a drawer, it gets stuck and it's sometimes hard to pull out. That same sort of thing can happen in the elevator, where it just makes it really hard to move because you're not reducing that friction. When you get more and more weight on it, you end up adding more and more of that friction force to the elevator, and it gets harder to move for your motors, so then your climber goes slow or may not even go up at all. So if you don't have bearings in the right spots, it can really harm the elevator design. So the design we're going to look at today uses these ball bearings in every kind of degree of freedom of the elevator to make sure we have really nice, smooth moving elevator. So here's how we kind of go about what it actually looks like and how we use them. So again, they're used to reduce friction, and the bearings are actually rolling on the tube. So this is what it looks like when it's not actually mounted together. So this is what we can kind of see one side of one of the stages. So we have these two bearings here that help take any lateral forces so that the stage of the elevator can't move side to side. And then we have these bearings here that prevent it from moving forward and backwards on the elevator, right? So this bearing is going to ride up this rail of the tube here, and then these bearings on the inside are going to be riding on this inside rail of the tube and spinning up and down. And so it's possible to replace any of these, like we said, with just like a plain bearing. And sometimes you'll see teams do that for these inner bearings, because a lot of times the side-to-side load on the robot is less than the forward and backwards. When you imagine you have like a full intake or something hanging off the front of the elevator, that's going to want to be twisting the elevator towards the front wherever you have that weight. So you definitely want to have these roller bearings here, but some teams will use non-rollers here and will just use kind of sliders or plastic on these side bearings. If you can design it to where they're all bearings, and most of the time it's sometimes even easier, we're going to buy these bearings in bulk. If we can make the design work, it's easier just to use the roller bearings a lot of the time than it is to try to also design some other smooth plastic thing, having to figure out how to mount it cleanly without any of the bolts or rivets touching it. There's a lot of other design work that goes into it, where if you can just use the roller bearings, it kind of solves a lot of those problems for you. So how do we actually power the elevator? So for Spectrum, there's a variety of different ways to power it. The ways that we power the Greyt elevator that we're using as our example, the way that we've powered our 2019 elevator, our 2020 climber, and our 2021 climber is all with chain and sprockets. There's a variety of reasons why we do it this way, but the biggest reason is it's just simple, effective, and we know it works. There are multiple other ways that teams have gotten to work in the past. Teams have used different ropes, different cables, any way that you can kind of wind up or winch anything, you could use to power an elevator if you wanted. Teams have used timing belt before. There's kind of specific kind of cord or rope that doesn't stretch very well called Dyneema. It's kind of made of a plastic, so it doesn't stretch a lot. So there's a lot of different ways you can make them. We've just found that sprocket and chain are very, very easy. They're simple to calculate in CAD to figure out exactly how long they need to be and where you need to mount everything. They're easy to understand. Most of you have used them if you've ever ridden a bike. You know how chain and sprocket works. You at least have an idea of it. You've seen it in your real lives. They're able to transfer really heavy loads because we have this nice steel chain. It does weigh a little bit more, but for most of the time, we're not too worried about that much weight. There's not going to weigh a lot when we're using the chain that we use. And it can handle a really heavy load. So lifting the entire robot when we need to do when you use it as like a climber or something, doesn't really affect the chain. It's easily able to lift the 150 pounds that the robot weighs. And it's also really easy to adjust the length and size and really easy to connect. We know we have spares of it. We're not having to worry about like tying knots in any sort of rope or anything. And so, and a lot of the products to do chain and sprocket are very common in the FRC marketplace. So a lot of companies sell sprockets for the various types of chain, the various shafts we use, the gearboxes we have. All of those types of things are all super easy. We're not having to create our own like winch drums or anything like that that other teams have to do when they're making these kind of cable rigged systems. When we're working with chain and sprocket, this is one of the things that we're going to need to do over some weekends. This will be some of the things that for any new students who haven't used it before, we definitely want to get some experience with before we get into build season. But there's a couple different tools that allow us to connect chain together and break chain. So when we have this like roller chain, we have to be able to push these pins out and reconnect them. It's not very difficult, but if you've never seen it before, it definitely takes a little bit of time to get used to and make sure you understand. But we'll definitely have some practice before we get into the build season in January. But these are some of those tools, and then we keep them all. We have a chain case where we keep all of our spare chain, a lot of the sprockets, and we have all of our chain tools in there, so it's really easy to grab and be ready to work on the chain. Back to kind of elevator specific things. If we have a moving loop of chain, so this gray block here represents chain, so it's not a fully catted, right? So this is, imagine it's just like this. It's all this roller chain in here. And we have it going down around a sprocket that's driven by a motor. So this is a motor and a gearbox. And we have this chain going down around. It's driven by that. It goes up, and there's another sprocket at the top that it loops over. And now we're just able to move this big loop of chain up and down the entire length of the tower of the elevator, of that first stationary stage. If that's moving, we have to somehow attach our first stage of our elevator to the chain. And so one of the ways that we do this, and the way they do this in this kit, is we have a chain clamp plate. And so basically, there's a little block here. There's a little spacer block. That's what this kind of bigger piece is. And there's a plate here. And we'll put bolts and nuts running through it, and it runs through the chain. And so then we just tighten them up, and we clamp that chain together. And so all of the force of the elevator moving up and down is going through those bolts and going through the force of it being clamped together and squeezed really tight. And this is basically how we do it for almost all of our robots. Is we'll somehow build kind of a clamping or interference fit to the chain to attach it to that first stage, so it can move up and down. Ooh, that's just incorrect. Sorry about that. That was a typo. All right, here we go. Okay. And so this picture has it again. You can see the chain is in blue, and there's the clamp block right there that attaches it. And so this has the full picture. This probably should have been a little bit farther forward. But so this blue chain is looping up around. This top shaft isn't powered at all, so there's no motor driving this specifically, but it's just powered because the bottom shaft is powered and the chain's there with the sprocket. So it's looped around. So this shaft doesn't move as the elevator goes up and down. This specific design has two chains. So you have a chain on the left and right side, and they're synced together with a shaft down here and up at the top. So we know that as these motors spin, you'll get that first stage of the elevator to go up. A very important part of every elevator system, no matter what you're using, whether you're using chain or some type of cable or anything else, is you have to somehow be able to tension it properly. With chain, normally, if you just have a full loop of chain, say we're using a chain to drive our drivetrain or an intake or something else where we just need two shafts spinning together at a distance and we have two sprockets on them and we wrap chain around them, normally we would just figure out the exact distance that they need to be depending on the number of links in the chain that we can do. So we have calculators for that. It's one of the things we'll go over in a few weeks. And they tell us exactly how far apart those shafts and sprockets need to be for the exact right amount of chain. And we have all of those lengths set up the way we need to. And over a short distance, that works pretty well. As we start getting over this bigger distance of the full elevator, you can imagine it's pretty easy that if you just did this length of chain, that maybe the mount down here, maybe this starts bending just a little bit, right? You can imagine this could bend up a little bit, and now this shaft is quite a bit closer to this top one, and your chain's getting loose, and there's no easy way to fix that. Since this plate is already bent, you could try to bend it back, but it's only going to do that so much because there's already that like tension because the chain is pulling against itself. So what we do is we have these chain tensioners. Here's two examples over here on the left. And they use a turnbuckle design. And what a turnbuckle is this middle part is basically like a really big nut. So it has threads on the inside of it. And these two outer parts thread into it. And what's kind of unique about a turnbuckle is normally, depending on how you set it up exactly, it can kind of be a turnbuckle if you don't. But most of the time when you talk about a turnbuckle, one side of the turnbuckle is going to be a left-handed thread, and one's going to be a right-handed thread. So a right-handed thread is what we normally use, where when we turn a screw to the right, it gets tight, and when we turn it to the left, it gets loose, clockwise tight, counterclockwise loose. The left-handed thread is going to be the opposite. So there's a few times on the robot, and there's a few different places where we do this. Well, we'll use opposite threaded things where to make it tight, we have to turn it counterclockwise or to the left, and to make it loose, we have to turn it to the right. And the advantage of that with this setup here is that we can kind of put it in loose, and we can design the system to where there's some of the threads showing on either of these things. They'll loosen up. And then as we need to tension it, we can just turn this in a single direction, and it'll bring the chain closer together, and it'll pull the chain tight. So we don't ever have to worry about the chain kind of skipping off of our sprocket, kind of like what would happen on your bike if your chain fell off your bike, where it kind of skips off the sprocket. We don't want that to happen in the middle of the match. So by tensioning that chain, we avoid anything like that where the sprocket can get loose. So this is a maintenance task that we'll do in the pit between matches. We'll check the chain tension, make sure it's still tight, and if we need to, we'll turn the tensioner or the turnbuckle to make it the correct level of tightness so it doesn't mess up in the middle of the match. So I don't actually know if we've talked about Versaplanetaries very much yet, so we're going to go ahead and do a refresher here. So Versaplanetary Gearboxes are a product from Vex Pro. They came out quite a long time ago now, back in 2013, and they've made different versions and improvements and things since then. But they're very, very useful. We use them especially for prototyping. They don't get all the way onto our competition robots as much anymore, but they're incredibly useful for prototyping because you can kind of build up the gear reduction you need very quickly, and you can also change the type of output shaft you have. So they have a lot of different features that allows you to do a lot of different things with them. The manual's kind of big, but you can see like there's different output shafts you can have, like different size hex shafts. You can have it imitate a sim motor, which is the same output as like the Rev Neo and some of the other motors we use. And you can kind of stack up all of these gear reductions to be able to build what we need. There's some disadvantages. It does have a lot of parts, so you can kind of see from this exploded view kind of what the gearbox looks like. There's a lot of little parts, and so like learning exactly how to assemble them all and get it all right takes a little bit of time. They're not too difficult, but they definitely take some work. This user guide's like 20 pages, which isn't too bad for what they're able to do. But they just give us a lot of options in how we can make, how we can slow down that motor from spinning really fast to being the speed that we need it to for whatever our mechanism is, because we're able to stack them. So like in this step, this only has a single stage, so this kind of like inner stage in here has the gear reduction in it. And it's all in a planetary form, which allows it to all be in a straight line, which is very convenient a lot of times. It makes it easy to mount, makes it easy to fit everything. And then we can add a second stage to it like we're doing in these instructions. So we can add in another set of gears, another one of these outside pieces called a ring gear, and we can mount the motor back in. And now we have a two-stage gearbox instead of a single-stage gearbox. And you can actually go up to a third stage sometimes, depending on what you need to do. They're they can take a bunch of different motors. We have a variety of motors that we can attach to them. They have different like input plates that you can put on. So they really just allow us to almost be like kind of like the Swiss Army knife of getting a motor to the right speed and right power and kind of torque output that we need, like force output for whatever the mechanism we're doing. So a lot of times when we're prototyping, if we're going to build like a test elevator, maybe if we're going to check something for an end game mechanism, or even sometimes when we're doing intake stuff, we can build these up really, really fast to be able to get mechanisms kind of tested and built, and we can know they're going to work, and then we can actually go in and design our belt and pulley or chain system or whatever we're going to actually use on the competition robot. In this case, they allowed them to have two of them very easily mounted to a single shaft. So they have these like couplers to mount to the shaft. And they get two motors being able to power up that elevator, so you get more, double the power of what you would only be able to do with a single motor. In modern FRC, because we have brushless motors, we have the Falcons that we've talked about multiple times, and the Neo motors that have about the same output power. You don't need this as much. A single Falcon can run an elevator pretty easily in most games. There might be a time where we need to. It just depends on kind of how much we're lifting or exactly how fast we need to lift whatever we're lifting. But most of the time, we're probably going to be okay with a single motor now for most FRC tasks. We kind of went through this already. Okay, so shaft collars, which I think we've used a couple different times in projects, but maybe not. But they're very simple, and if we haven't, I would definitely want to cover them. They allow us just to clamp onto a shaft. Normally, in these cases, these are hex shaft collars, so they fit all around like a 1/2-inch hex shaft. And then we just tighten the bolts here, and they'll clamp to where they can't move back and forth. So if we need to locate a sprocket or a gear onto a shaft somehow, shaft collars do a really good job of that. So here we have the shaft collar right in front of this sprocket. So then once this whole thing is mounted up, it prevents this sprocket from being able to slide back towards the motor, which we wouldn't want it to do. We wanted to keep it in a nice straight line so that the chain stays on the sprocket the whole time. But if we didn't have that shaft collar there, it might slide back. You could also do this with like a spacer. There's a variety of other ways you can do it depending on exactly the application. But a lot of times, especially in our prototyping, we will get shaft collars in place to keep sprockets in place, pulleys in place, wheels in place, anything that we need to have along a hex shaft that we don't want to slide back and forth along that shaft, and we just want to locate it or keep it on the shaft. Shaft collars work really well as we're building up mechanisms and getting them tested and ready to go. Kind of the bigger version of a shaft collar is a shaft coupler. So these allow two shafts to be connected. So in this case, we have the output shaft of the Versaplanetary, and we have this extra piece of hex shaft right here. And they both slide into the shaft coupler. We tighten down these 8 screws all the way around it. And those two shafts are going to stay connected together. They're not going to be able to slide back and forth. They're not going to slip apart from each other. And they're going to turn together so we can keep the sprockets in sync with each other. So both sides of the elevator go up at the same time and then come down at the same time as well. Okay, so we've talked about how we move this outside or this first stage of the elevator, but we haven't talked about how does the carriage move. And so this is where elevators get a little bit more confusing, and you have to kind of look at it a little bit more in detail. So we do these setup that we use most of the time for any of our elevators if we need to have a second stage. And the elevator that we're looking at here are set up in a configuration known as a cascade elevator. So the chain that's moving from the motors is only powering that first stage up and down. And we're going to use the relative motion of this first stage and like the fixed position of the of this tower part of the fixed stationary part of the elevator to be able to move the second stage of the carriage up and down as well at the same time as that first stage moves. So here we can kind of see what the Cascade Connection looks like. So the Greyt elevator uses a cable. Most of the time when we've done it on our team, we've used another chain run that works too. Teams have used like nylon straps. You can use different rope. You can kind of use whatever you want as long as you can make it into a loop. And the important part of this is that we have a connection right here. So this is going to be a fixed connection, so the cable can't like slip through this at all. If you pull this up or down, the cable's going to try to like spin around here. If I try to move this carriage up, the cable's going to come up here. And then I should have got a better picture. And so then there's another loop. There's a pulley up at the top here and at the bottom here. So this allows the cable to kind of slide past it and roll past it on both ends. And then right behind this bar is another fixed connection for the cable. So we'll mount the cable is fixed here. It's fixed here on the carriage. And so then as this first stage moves up, because this part of the cable, this pulley, is getting further away from this fixed point right here, it's basically acting like it's pulling down on this cable because more of the cable has to be like kind of wound out and put onto this side so that the carriage is going to go up as this first stage goes up. And so this is how we did it in our 2019 elevator. So you can actually see back here, as the elevator goes up, the first stage and the carriage actually go up at the same time. So it's not like one goes up and then the second one goes up. They're both moving at identical speeds. So for every inch that this first stage moves up, the second stage moves up an inch relative to kind of the bottom of the first stage. And you get your full height that way. The other version that I don't have a graphic for is called a cascade. It's called a continuous elevator, and that allows you to move them kind of independently, depending on what, how much force and friction is there driving the carriage in the second stage. So if we need to go, if we're just doing a single stage where we don't need a carriage, so the carriage lets us get to the floor in case we need to intake game pieces or something. But in our 2020 robots and 2021 robots, we didn't need to do that. So this is our 2020 robot. And so we just needed to be able to do a pull-up. So it had its hooks all the way at the top of the first stage, and there's no inner carriage or anything. So kind of pulling into here a little bit more, you can see this is where the sprockets are. So there's a shaft here that's not showing up in CAD that it's spinning around. There's a sprocket down here. There's also some missing parts in this one. So there should have been a shaft being powered across this bottom to where both of these chain runs are being driven up. Here's kind of that mounting point. You can see the screws that mount the chain right there. Yeah, the clamp plate. So we're going to put those bolts through there, and we're going to clamp the chain right here. And then as we spin this motor down here in this shaft, that whole thing goes up. This comes pretty high, and we eventually are able to hook onto the bar and reverse it and have the robot climb. In our 2021 robot, we kind of made that whole system even more compact, so it's a little bit harder to see. So we have the bottom sprocket way down in there. We have a top sprocket up here. Oop, I zoomed in the wrong spot. We have a top sprocket up here behind these two plates. And then the chain is running between these tubes here. So it's running up in between. And then way down here, we have our clamp plate. So this is actually not how we ended up doing it. So this is how we drew it originally. We thought we were going to bolt kind of through here with some spacers. But we ended up realizing that doesn't work. You couldn't replace the pins in the way that we thought we could. So we ended up bolting with a clamp plate going through the chain this way into the inside of this tube. So we actually bolted into the inside of that tube, which was kind of annoying, but not too bad. It's pretty close to the bottom of the tube. I think we actually did it pretty low. I think we did it down here. So then as that moved, when we take it out or up, I think this should be able to move. Yeah, so this, part of that moves. Let that move in a weird, that's odd. I think there's like a second elevator for some reason. All right, I'm not entirely sure what's going on there. Something's not constrained right on this model, but that's fine. So we can still see part of what's happening. So as this slides up, we can come all the way up to the top here. What part is that? That is climber. I don't know why there's a second. Huh. Okay, let's hide this real fast. Something got a little odd there that shouldn't exist. Okay. So yeah, so this looks better. So this is moving up and down, and so that goes all the way up to its like highest point there. This allows us to reach up, hook onto the bar, and then when we drive the chain back down, so that clamp plate would stay here. It would be right in here, and it would mount into it would mount through the tube here. I think we actually might have bolted all the way through, actually, now that I think about it. I think that's what this part is for. Oh, yeah, so that's what this part is for. So this was 3D printed, and this went into the inside of this tube. And then we were able to stick bolts all the way through and have the nuts come out on this side to have it mount up and down, and it was able to roll. And so this elevator we actually ended up not using bearings in both directions. So we have bearings here that are sliding across, that are rolling across this face of this tube. And then because of the sizing and exactly what we were trying to do, we ended up having these pieces of plastic here that are actually just sliding against this side of the tube. So these aren't spinning at all. These aren't rolling. These are just sliding with kind of limited friction. But because we don't have a ton of side load on this anywhere at the moment, it works okay just to slide up and down. If we were using this as an actual scoring elevator where we're going to be doing it multiple times a match, we probably wouldn't do it this way. We probably would have made sure to have rolling bearings in here. But just because we could, we knew we only had to climb, we had more than enough power to do that. If we had a little bit of extra friction, it wasn't as big of a deal. We weren't too worried about how fast this motion was. It just needed to be fast enough to climb at the end. Where in our 2019 elevator, where we're using this to score every single time we're doing it, we're moving that elevator a lot more times a match, and it's slowing down our entire cycles. We're moving it up and down. 1, 2, 3, 4, 5, 6. Yeah, close to, anywhere from 6 to 12 times a match, we're probably moving that elevator up and down. If that doesn't move fast, it's a much bigger problem than our end game solutions that can move a lot slower and lift the whole robot.